Hello everybody. This video presentation from Industrial Systems Institute aims to demonstrate the achievements related to scene analysis and understanding, different odometry solutions, as well as cooperative localization approaches. Dr. Aris Lalos, Principal Researcher at ISI and Head of MIPS Group, is responsible for the provided info.
This video demonstration aims to present the progress on multimodal scene understanding within the context of CPSoSaware. The basic physical ecosystem of the autonomous car incorporates, among others, GPS, LIDAR sensor, and cameras. For this part, only video and LIDAR sensors are used. "3D LiDAR point cloud data are processed by point RCNN detection network, generating three-dimensional bounding boxes. Furthermore, 2D imaging data are processed by the squeezed detection network. The fusion process takes place as follows. Initially, we project 3D bounding boxes and the corresponding 3D points on the two-dimensional image. Secondly, we use the points whose projections lie within the 2D bounding boxes generated by squeezed. The union of both detection outcomes takes place. For the training and evaluation, the Kitty odometry dataset was used. 7,485 point cloud scenes, along with the corresponding imagery, were used. 3 classes are considered: pedestrians, cyclists, and cars. This video demonstrates the fusion of 2D and 3D detection outcomes on Kitty dataset. Green points correspond to LiDAR-based detections, while red points to 2D image-based detections. However, the main drawback of existing datasets is that they confine the accuracy of the train detectors in the conditions that were originally recorded. As a result, Carla Simulator was employed. 4,426 training images were used, along with the corresponding Velodyne point cloud data. This video demonstrates the fusion of 2D and 3D detection outcomes on Carla Simulator. Likewise, green points correspond to LiDAR-based detections, while red points to 2D image-based detections. Further improvements are also considered. They will involve an improved fusion strategy, taking into account the accuracy of each detector per class. Furthermore, fused region of interest training for both detectors will also be investigated. Finally, evaluation in different weather conditions will also take place, deploying appropriately the simulator. The following slides present scenario simulation with respect to object detection. Scenario 1 involves 2 vehicles and 2 pedestrians. Vehicle B is driving straight with speed less than 30 km per hour, while Vehicle A is driving straight with speed less than 30 km per hour and reduces speed to turn right. The expected behavior is that Vehicle A and Vehicle B detect the moving pedestrians P2 and P1. Here, we can see an overview of Scenario 1. Vehicle A is turning right while 2 pedestrians are crossing the street. Vehicle A is turning right while 2 pedestrians are crossing the street. Pedestrian P1 is being detected by Vehicle A as it turns right.
this use case scenario, we focus on the aspect of operator safety, trying to reduce their body strain by performing biophysics assessment for their ergonomic optimization. We assume that the successful implementation will be able to change or adapt the robot's configuration, for example, the height of the windshield, based on the monitored operate state that is received in a real-time mode. For the implementation, the OpenPose algorithm is used, which it has been trained in the COCO dataset of images. It can combine pose, face, and HUD estimation of landmarks. It can be used offline in pre-recorded video or in real time using camera. It provides JSON files output with the coordinates of the landmarks and a confidence rate that can be used for the evaluation, and also it can be used both in automotive and in manufacturing pillar. In this demo, the implementation of the algorithm for the pose estimation is presented, applied to the CRF simulator that shows some typical tasks and actions of the operator in the workplace. Vision capturing systems are used for the detection of the operator's pose in order to perform a proactive ergonomics optimization of the equipment. More specifically, the system has to identify the anthropometric dimensions of the operator in order to adapt the optimal position of the windshield for the operations to take place, and also it can provide relative warnings and suggestions. The next steps are to automatically select the best view of camera based on the confidence value received by the algorithm's output, to evaluate the pose recognition output with the ground truth landmarks of the 3D avatar model, which have been predefined via the simulator, to be tested in a real industrial environment using the output of cameras capturing movements and action of the worker while he or she performs typical operations in the workplace. And also in this case, the evaluation will be performed through the multimodal approach using a whole body tracking system and IMUs, assuming that they provide ground truth values.
Hello to everyone. This video presentation is about robustifying different odometer solutions and effectively realizing cooperative awareness for connected and automated vehicles, both developed by the CPSoSaware project. For real-time implementation of the different solutions, Lalos framework has been exploited. Furthermore, RQT and RVs are utilized in order to plot the error of the different position solutions, as well as to visualize the trajectory of vehicle. The main assumptions that we have followed is that the ego vehicle follows a predefined path inside Carla simulator, in which different weather or lighting conditions may occur. In order to estimate the position of vehicle, 3 different algorithms are utilized based on camera sensor, LIDAR sensor, and GPS of cooperating vehicles. The first solution is known as direct sparse odometry, and it is a visual odometry-based method. It mainly focuses on localizing the camera sensor, which is integrated to the vehicle, and map the unknown environment in which the vehicle is interacting. As you can see in the video, green trajectory corresponds to the DSO output, while the red trajectory is in fact the ground truth. Well, DSO is able to achieve a very good positioning accuracy. Furthermore, white points correspond to the detected landmarks by the DSO, which are in fact some interesting points in the image plane. As you can see, DSO is very close to the ground truth. while the vehicle is moving inside Carla. However, its accuracy may be affected in diverse weather and landing conditions, or in the case where some neighboring vehicles are also moving. Okay. Now let's proceed to the second solution, which is known as LEGO-LOAM, and it is a LIDAR odometry-based method. LEGO-LOAM extracts from raw point cloud planar and edge features. The former are used to estimate the translation of z-axis as well as the roll and pitch angles, while the latter are used to estimate the translation of x and y axis and the yaw angle of the vehicle. By using these types of feature points, LEGO-LOAM performs a two-step Levenberg-Marquardt optimization method in order to get the 6 degrees of freedom vector, which describes in detail the position of vehicle. So, as you can see in the video in the right side, the red rings correspond to the raw point cloud, which is which is used by the LEGO-LOAM in order to estimate the position of vehicle. As you can see, LEGO-LOAM's trajectory is very close to the ground truth, which means that using only the LIDAR sensor, vehicle is able to position itself. Different colors in the environment correspond, in fact, to these two types of features, namely planar and edges. Of course, as it is also the case in DSO, LEGO-LOAM's accuracy may be seriously affected in different weather or lighting conditions. In any case, it is apparent that LIDAR and also camera are able to be used in the case of localizing vehicle. You can see the vehicle is always moving, and LEGO-LOAM generates a trajectory using the point cloud. Okay. Now, in this video, we plot the absolute pose error and the relative pose error of both rotation and translation of DSO and LEGO-LOAM. DSO is better than LEGO-LOAM in the case of absolute pose error, while LEGO-LOAM is better in the case of relative pose error. That means that LEGO-LOAM has a much better tracking ability than DSO, which may be useful in harsh environments in order to estimate the position of the vehicle. Note that these peaks of the error are mainly due to sharp turns of the vehicle, which affect the performance of the two methods. Okay, now we have also the case of night driving. As you can see, the error of both methods is lower than 2 meters. And once again, DSO, by using only the camera sensor, outperforms LEGO-LOAM and generates the pose for the vehicle. Okay. So the third solution is based on the so-called cooperative awareness for connected and automated vehicles. For this task, we have developed and formulated a distributed scheme for localization and tracking of moving vehicles by exploiting the cooperation between them. The focus of the scheme is, in fact, on estimating vehicle location as well as its neighbor's position, quite accurate. Also, this scheme has been implemented using the Carla-Ross framework. Its main idea is the so-called Laplacian processing technique, which enables the effective multimodal fusion of 3 measurement modalities through the linear Laplacian operator, which encodes the V2V connectivity of cooperating vehicles. Extended Kalman filter algorithm has been also used in order to design the tracking method. Vehicle extracts range measurements to nearby vehicles from visual features And additionally, it receives from its neighbors using V2V communication their 2D GPS position, linear velocity, yaw rate, yaw angle, as well as the vector of range measurements towards their own neighbors. That means that justifies actually the need for data association, which means that we have to match the range measurements to the correct vehicle ID coming from V2V communication. As you can see in the figures, the yellow vehicle collaborating with its neighbors using, of course, communication, vehicle-to-vehicle communication, is able to estimate its position as well as the position of its neighboring vehicles. Okay, now we plot the error of cooperative localization using extended Kalman filter and Laplacian processing with respect to DSO. In the case of ego vehicle, as you can see, ego vehicle interacting with its neighbors is able to estimate its position much better than DSO while it is moving. Note that the peaks of the error are mainly due to the fact that the noisy positions of neighbors have been modeled using the Gaussian distribution. However, as you can see, cooperation leads to a much better positioning accuracy, and as it will shown in the next video, it will also contribute in the cooperative awareness ability of each vehicle. Okay, now let's move. Okay, now we have the case of cooperative awareness evaluation. Green light above the vehicles correspond to the fact that ego vehicle estimates neighbors' positions better than the received GPS measurements, while the red light actually means the opposite. Furthermore, we have plotted the number of neighbors of ego vehicle for each time instant, as well as the average GPS and cooperative awareness error of its own neighborhood. As you can see in this case, average cooperative awareness error is much better than GPS, meaning justifying the increased ability for cooperative awareness. Following the cooperative localization, following the proposed cooperative localization approach of CPSoSaware. Okay, now we have the ego vehicle that is moving, and apart from its own location, estimates also the location of its neighbors, much better than GPS in most of the cases. As you can see there, ego vehicle has, at those time instances, ego vehicle has no neighbors, and therefore a different solution should be followed using, let's say, DSO in order to estimate its position. And when a new neighbor is found, as it is this case, the cooperative localization approach is now running again. Ego vehicle estimates well enough the position of neighbors. Red light appears only in the case where cooperative awareness and GPS difference appears only the case when the difference of GPS and cooperative awareness is very small. However, in most of the cases, ego vehicle estimates quite accurate the position of its neighbors, realizing effective cooperative awareness. Okay, now finally, we have developed also a V2x simulator as a standalone ROS2 node in order to realistically model the cooperative localization approach, exploiting realistic V2V communication with among the vehicles. The V2x simulator supports also Carla simulator, and it allows the selection of different propagation models in order to realize a high level of realism. Okay, here we have some some details about the integration of V2x simulator with the proposed cooperative localization approach using extended Kalman filter and Laplacian processing. We have also some general info about the selected vehicle. As you can see there, we have its name, its speed, its steering angle, etc. We have the related V2x messages transmitted by its neighbors and received by the selected ego vehicle. And finally, we have the results of cooperative localization, of the proposed cooperative localization method, where, as you can see, cooperative localization error achieved by the method is much lower than the GPS, even in the case of realistic V2V communication, where, for example, network delay may affect the performance of localization method. Okay, we have also a video demonstrating the applicability of the integration of the simulator with the cooperative localization approach. As you can see, the simulation is now started. Okay, let's proceed. Okay, now we have the vehicles that are moving. As you can see, all the vehicles have the V2V ability and in fact communicate, every vehicle communicates with all others. We have also some info about the path loss of communication, which may seriously affect the communication. And now we start running the proposed cooperative localization method, which means that each vehicle runs now this approach in order to estimate both its position as well as the position of its neighbors. As you can see, in most of the cases, although, for example, network delay may be present, each vehicle is able to estimate its position. And as a next step, we are planning to evaluate also this approach in the case of cooperative awareness. Okay, that's all from my side. Thank you for your attention.